Okay, so now we start solving the exercises on permutation groups. So this first one is we of course made this up, and this will address that issue that we came across in the text, where the author tries to prove that a given permutation is either an even permutation or an odd permutation, but never both. So in doing that, recall that he introduced one polynomial in n variables. If the group we are working in is the symmetric group of degree n, then he considered this polynomial in these n variables, whose definition is this. It's the product of all factors xi minus xj, where I and j vary from 1 through n, satisfying the restriction that I is less than j. And in fact, a concrete example was given when n is 5. So then after that, the author mentioned that if one applies any permutation theta on the polynomial, in the sense that the permutation will be applied on the suffixes, then we get either the polynomial itself or its negative. In particular, if the theta that we are applying is a transposition, is a 2 cycle, then p theta, that is after you apply theta on the polynomial, you get the negative of the polynomial. So now we need to verify this. So let's see what we can do. Note one thing, that if you manage to prove this, then this one will automatically follow. Why? Because any permutation theta is a product of 2 cycles. So you can apply that product of 2 cycles on this p by applying 1 2 cycle at a time. So you will get minus p, then again minus of minus p, you get plus p. So that way you will either get minus p or plus p. So we start off by mentioning that since every permutation is a product of 2 cycles, that means transpositions. It's enough to prove that p theta is minus p for any transposition theta. And that's what we are now going to do. So let theta equal to I comma j be a 2 cycle or a transposition. Where these I and j are of course some symbols lying between 1 and n, and they are different of course, otherwise it won't be a 2 cycle. So we can conveniently assume that 1 is less than or equal to I is less than j, and j is less than or equal to n. If you want, you can switch I and j also, it will not make any difference. Okay. Now we need to look at the polynomial and identify those factors in the polynomial that will actually be affected by theta. There will be some factors which will not be affected. Clearly, the factors that will be affected, the factors look like what? They look like this, no? X alpha minus y beta, where alpha and beta are just like this, like I and j, some integers lying between 1 and n, and alpha is less than beta, because that's how we are, that type of factors we are allowing in the polynomial p. So now this factor will be affected by theta provided either alpha is I or j or beta is I or j, because you see, what does this theta do? It changes I to j and j to I, and it keeps all the remaining symbols here from 1 through n fixed. So that is why, unless these suffixes themselves are either I or j, this factor will not be affected. For example, if our original, say in the example that we considered in the text, there we had n equal to 5, right? 5 is a little, okay, anyway, n is equal to 5. So if we take I equal to 2 and j equal to 3, so this is my I and this is my j. That means I am considering this transposition. Then in our original polynomial, which will then be in 5 variables, that will have a factor which looks like this, x4 minus x5, and it will also have a factor which looks like this, x1 minus x5. This type of factors will not be affected by theta, because this transposition does not do anything to 4 or 5 or 1. So these factors will stay the same. However, factors like this will of course be affected. For example, x2 minus x5. After applying theta, this will become x3 minus x5. Or for example, x3 minus x5. This will become x2 minus x5, and there is precisely one factor where both the suffixes are getting affected. x2 minus x3 will become x3 minus x2 after applying theta, because we are swapping 2 and 3. So we now need to look at the types of factors that will be affected. Those which are not affected at all by theta, they need not be considered. They are there initially before applying theta. After applying theta also they will be there unchanged. Okay, so let us now look at the factors that will be affected. And there too, while listing the factors, we will not just haphazardly list them, but we will use a little classification to write them neatly, and it will help us also. Okay, now theta affects precisely the following factors of P, and in this context, following factors means linear factors. Okay, we are just simply using the word factors to mean those individual things, linear polynomials. Okay, so let us start. The first type of factors is the one where the factors look like this. Note one thing, it's I think better to clean this part. You see, the symbols are like this. No? You have 1 here, then 2. At some stage, you have I minus 1, then I plus 1, and then it increases further. At one stage, you have j minus 1, j plus 1, and so on up to n. And we have I first and then j because I is less than j, and we are writing the things down in this manner. Okay. So what I am now going to do is that because the suffixes in the x's that whose differences we are talking about here, those are the linear factors, they should contain either I or j. They should be either I or j or both. So we first look at those factors which contain only I. Okay. That too, there will be 2 types of factors. The first one will of course be factors which look like this: x1 minus xi, x2 minus xi, and so on, xi minus 1 minus xi. So that means we have used these things with I. And note that these factors will actually appear in the polynomial because all these first coefficients are less than I, starting from 1 all the way up to I minus 1. And then come the factors where where also we have I, but the other suffix is all greater than I. So we classify it as a second type because the first suffix should be less than the second suffix. So this time we start with xi minus xi plus 1, then xi minus xi plus 2, and so on, xi minus. When we reach this place, we have to be a little careful because what we said just now is that we are writing down those factors where the suffixes have just I but not j. So we have to carefully not consider the factor xi minus xj. So at some stage we will have this, and then xi minus xj plus 1, and then of course xj plus 2, those things will come, and ultimately we get xi minus xn. Okay. So these are all the things where we will have only I, and then of course we can just simply mention this and the job will be over. There is a single factor which has both I and j in the suffixes. Then the fourth type, j. Okay, if the suffixes have only j and not I. So here, just like before, but again we have to avoid xi. Already we have accounted for it here. So that means xi minus 1 minus xj xi plus 1 minus xj, and then xj minus 1 minus xj. Then when we write the higher suffixes, you have to of course start with j, because j is less than j plus 1. Always keep this in mind, that whatever factors you are writing, the first suffix should always be less than the second suffix, because that type of factors only we have in the polynomial. And then let me write one more, xj minus xj plus 2, and finally xj minus xn. Okay, so these things will be affected. Now after applying theta, what do we get from these? I will become j, j will become I. After applying theta to P, the above factors become, let us start with here. Number 1, I becomes j, x1 minus xj, x2 minus xj, and so on, xi minus 1 minus xj. Then number 2, so this we have already written what happens to them. Then number 2, here I will become j, all the others will not change. Don't there is a chance of making a terrible mistake. You may think that because j plus 1 is appearing here, you should change this j to I. No, this is some number, some suffix which has been expressed in terms of j in this way because it's convenient to do so, and it keeps track of what is happening and which one is where. This number itself does not have anything to do with j. Only in this representation you see it, you find it as j plus 1. It is just something. Okay. You just simply, wherever you see the suffix I alone, you change that to j, and wherever you see j alone, you change that to I. That's the thing. So this will become xj minus xi plus 1, xj minus xi plus 2, and so on. Here again xj minus x j minus 1, so that means we have reached j minus 1, and then xj minus x j plus 1, and so on. Others of course are there, the next one xj minus xj plus 2, and finally here we have xj minus xn. Let us first complete writing these things and carefully, and then we will see where we can go from there. For this single one, of course, this will be xj minus xi. Okay, and then we come to the ones containing only j. 4. So now j's will become I. x1 minus xi, x2 minus xi, and like that one goes, and finally gets xi minus 1 minus xi. Yeah, because this becomes xi, and then the thing continues, xi plus 1 minus xi plus 2 minus xi, and so on. At this stage we get xj minus 1 minus xi, again don't change this j to I, and then xi. Oh, see, then here something else is happening, because you see what happens here. We started varying the suffix from 1 through j minus 1. Okay, so all of them were less than j, so the factors look like this. But in the next one, j plus 1 is encountered, which is greater than j, so we had to change the position of xj. Now the things are not ending with xj but beginning with xj. So here correspondingly we have xi minus xj plus 1. I wrote one more, huh? So xi minus xj plus 2, and finally xi minus xn. Okay, now we need to see which factors can be just simply kept the way they are, and which factors have to be changed, in the sense that we don't really need that factor, but rather we need its negative. The reason being that in some of the factors, after they have suffered these changes, the first suffix has become greater than the second suffix. That is the problem, because that factor originally will not be in our polynomial, but rather its negative will be in the polynomial. So let us see. There is no problem with these x1 minus xi, because here you see all the suffixes starting from here all the way up to I minus 1. These first suffixes are all less than I. So that means even after changing things, even after applying theta to p, and you are now looking at these changed factors, they do not offer any difficulty. They can be just simply kept like this. So they ultimately do not affect anything. Okay, so this part does not affect anything. Now let's look at this one. Here also things are going very well. Okay, so here also there is no problem. Have I made a mistake somewhere? Let me just see. Oh no, what the hell? These are actually the original things. After applying theta, I have written these things now. See what I was thinking. So you see, so that means whatever I was doing there, I should have said about this part. Okay, so let's again look at this. 1, 2, 3, etc. up to I minus 1, they are all less than I, like what we noticed here. But I itself is less than j, so all of them are also less than j. That means these factors will stay in our polynomial the way they are appearing here. There is no problem. The first suffixes are all less than the second suffix. Okay, so this part does not offer any difficulty. It's okay. When we come to this, however, there is a problem. In this second class of factors, that too, the entirety is not a problem, The problematic part is this much. Because you see here the first suffix in each case, which is j, is greater than the second suffix. In fact, here the second suffixes are increasing, I plus 1, then I plus 2, I plus 3 and so on, and it reaches this maximum value j minus 1, that is also less than j. So they need to be negated. We have to consider their minuses in order to fix things. After this, in this second class of objects, the other things offer no difficulty because these are okay. In them, the first suffix, which is j, is less than the second suffix. Okay, so we have encountered problematic factors here in this region. This, of course, is a single one, but it is problematic because j is greater than I. It also has to be negated. In the fourth class of factors, we start off and there is no problem. This part has no problem, x1 minus xi, x2 minus xi, because 1, 2, 3 all the way up to I minus 1, they are all less than I, like what we see here. But the problem starts from here, I plus 1, then the next will be I plus 2, j minus 1, etc. These are all greater than I. So this much is problematic again. But just like the second case, here things end with having non-problematic things. Starting from this one up to this, there is no problem. I is less than all these second suffixes. So there are three regions of problems. One is these factors, one is this single factor, and the other one is these factors. Each one of them has to be negated in order to retrieve P back. Of course, with a possible plus or minus sign. So we are now going to decide whether plus will occur or minus will occur. That will depend on exactly how many negations we have to do. And there is one more thing. You may be thinking that, okay, plus and minus are fine, but factors themselves are getting changed. No. For example, this x1 minus xi now has become x1 minus xj. But does it not mean that we have lost one factor, x1 minus xi? Because if that is so, then just simply sign changes are not enough to get back P. No, if we have actually lost factors, but we have not lost factors, just like in place of x1 minus xi, we have got x1 minus xj. Somewhere we have x1 minus xj also. That has changed to x1 minus xi. So it's just shuffling, not taking things out. So we don't really have to think of losing factors or gaining some extra unknown factors from outside. Whatever we have in the polynomial, again actually we will have those same factors. The only thing is that maybe after applying theta, the new factors actually will be old factors or their minuses. Okay, because you can see that way the things are working here. So we will of course either get P or minus P, but now we are going to decide which one it will be. So to retrieve P back from P theta, we need how many sign changes? That now we have to calculate. that will be determined based on how many problematic factors we have. Okay, you look at these first ones, they look like what? xj minus xi plus 1, then xj minus xi plus 2, like this we reach xj minus xj minus 1, but I am not writing j minus 1 just like j minus 1. I am going to write that in terms of I, that is, let me just not write this second one, get some space. Instead of writing the last one as xj minus xj minus 1, I decide to write it as xi plus j minus I minus 1. This will serve a purpose. It will tell me exactly how many elements are there in this list. The first one is having xi plus 1, the second one is having xi plus 2, and this last one is having xi plus j minus I plus 1. So this number that you see, which is whose sum with I has been taken, that actually gives you the number of elements in this list. So there are j minus I minus 1 polynomials or factors in the first problematic region. What about the second problematic region? Here also, if you apply that same technique, xi plus 1 minus xi, instead of writing xj minus 1 as j minus 1, you write it as this, minus xi. So here also we have j minus I minus 1 number of factors. Previously also we had that same number of factors, but there is one more, this extra unique one. So that many sign changes we need in order to retrieve or get p back from p theta. So now we are going to write. We need 2 times j minus I minus 1 plus 1 sign changes. That means sign changes means that many minuses have to be taken out, and the factors, thus these factors, each one of them, the problematic ones, are fixed. Like for example, in place of xi plus 1 minus xi, actually you will write xi minus xi plus 1. So the first one becomes less than the second, but then for that you get one minus. For this one you get another minus. So this many minuses, minus 1s you will have, which are multiplied together. So minus 1 to the power this. Now note that this is an odd integer, and that is why whatever this j and I are, it does not matter, you will get minus 1. And that's why p theta is minus p. Hence, instead of explaining those things, which is almost self-evident, having gone through this, it's now, and having written this thing down and about mentioning about sign changes, it now becomes clear that we have p theta equal to minus p. So that's just it. And you see, that is why in an even permutation, there can only be an even number of transpositions, because when you apply the permutation as a whole on P, those transpositions will be applied. So you will ultimately get plus P, and in a possibly different representation of the same permutation, again as a product of transpositions, the transpositions themselves may be different, the number of transpositions also may be different, but they should be even in number, because otherwise the function, I think I mentioned about this in the previous video also, otherwise this function which takes us from P to plus or minus P is not well defined. I mentioned about the need to show that this function is well defined, which strictly speaking I have not done here, but I leave that to you. Okay, you convince yourself that the function theta applied on P and getting this thing is actually a well defined function. It's not very difficult to conclude and see why that is so. Okay, that I leave to you. If you don't get something or you get stuck somewhere, please let me know. Okay, so now we can start the actual exercises. Number 1, I need ink. Find the orbits and cycles of the following permutations. There are 2 are given. The first one is this. Oh, it's long. 2, 3, 4, 5, 1. Six, 7, 9, 8. B. There are some things which are often overlooked or forgotten about. So let me just once again remind you of some things about these symbols. The symbols look like something, look like a matrix or something like that, but actually they are functions, don't forget that. In fact, they are one-to-one onto functions, that is bijective functions or permutations. That's why they are called permutations. One more thing is that these are not numbers, these are objects, or rather the elements of the set on whose permutations we are considering. For example, in this one, actually we are considering some set of objects. Now because it's cumbersome to keep writing x1, x2, and because we really are computing with the suffixes, that's why we choose to write 1, 2, 3, etc. in places of x1, x2 and x3. Okay, so working with these things, you may forget the fact that these are just symbols, and that's why we use the word symbols 1, 2 and 3, and we don't say positive integers 1, 2 and 3. Okay, this fact is easily forgotten, but please keep it in mind. Okay, so now we have to find orbits and cycles. We already know what those things mean. Orbits you may have forgotten, but cycles, of course, we have been dealing with them for a long time. Orbits are just what the function does to one thing and then keep doing to its images, and whatever we get as a result of that, that is the orbit. The orbits are, so let us start with one, and keep in mind the orbits are just ordinary sets. 1, then the permutation sends 1 to 2, then it sends 2 to 3, so 3, then 3 is sent to 4, 4 is sent to 5, and then 5 is sent back to 1. So that's just it. This is one orbit. Orbit in the sense that you can think of, we already discussed these things before. You can think of the permutation as a sort of force which you are applying on an object that is moving, and these are the positions of the object. So if the object is at the position 3, at the location 3, then in the next stage it will be at 4, and then it will be at 5, then again it will be at 1, and it will keep on cycling like this and taking these positions continuously. So that in that sense it's called an orbit. Anyway, so this is one orbit. Another orbit is this singleton set 6, then this singleton set 7, they are not changed at all, and here we have 8, 9, and correspondingly from the orbits we have cycles, right? So the cycles are and 8, 9. Cycles have precisely the elements of a given orbit, but cycles are different from orbit in that cycles are ordered sets. An orbit, although we write like this to conveniently see what is happening with the elements, like for example theta sends, if you want to call this permutation theta sends 1 to 2, 2 to 3, etc. But because it's a set, order actually does not matter. But here order matters, and in a very precise way it matters. Not in a linear way, but in a cyclic way. The cyclic order should be maintained. Even if you write 1 here, there is no problem, but after 1, 2 has to appear. After 2, 3, and then after 3, 4, 5, and then 1. So anyways, so these are the cycles. These are one cycles which we usually do not use while writing permutations, but nevertheless they are also cycles. Okay, so the second one likewise here. The orbits are what we start again. It also does not matter where you start. 1 is sent to 6, 6 to 2, 2 to 5, then 5 goes back to 1. So this is one orbit, and there is one more, 3 to 4 and 4 to 3. So the cycles are, let me write this one first, and 1 6 2 5. In the next one, I think we are being asked to, yes, exercise 2. Oh, I did not write exercise. Anyway, how many times shall I write exercise? Let me just simply write 2. Write the permutations in exercise 1 as products of disjoint cycles. Okay, and you already know how to do that. You just take the product of these cycles that you have found, that will give you the permutation. And the way we find orbits and hence cycles from them, these are of course also disjoint. No two of them have any common symbol. The first permutation is, that means this one, is 1 2 3 4 5 times 8 9. We already know there is no point writing a one cycle. By convention, we know that if a symbol from the set of symbols on which the permutations are acting is not present here, it just means that the permutation keeps that symbol fixed. And the second one is the product of these two. And just one more small thing, because the cycles are disjoint, they commute. So it does not matter which you write first and which you write second, or in case of having many cycles, which order you use to write the product. That does not matter. As long as the cycles are disjoint, that is immaterial. Next, express as products of disjoint cycles. 1, 2, 3, 4, 5, 1, 6, 7, 8, 9. And 1, 5. These are not disjoint. P1, 2, 1, 2, 3, and 1, 2 again. Okay, so we will do it at once. At once means we will write this down, and from that we directly write down the disjoint cycle decomposition because it's very easy. We have this equal to, okay. Now, how shall we calculate the product? I mean, which order should we follow? Should we start from this side and then move towards the right, or should we start from this side? That will depend on your notation of functions. Because these are after all functions, each one cycle itself is a permutation or corresponds to a permutation in a specific, there is a specific meaning to that. So that means these are compositions of functions. 4 functions are involved here, which you are now going to apply on these symbols and see what happens. And that see what happens, that thing, then again you will write in terms of permutation or cycles. So if you are using your ordinary function notation fx, f of x, then your f is the function, this function. So your x will lie on this side. That means you will have to start your calculation from this side, because this 2 cycle, which is after all a function, a particular type of function that maps 1 to 5 and 5 to 1 and keeps all the other symbols fixed, that you are applying on x first, and then on the result you are applying this function, and then so on. But in this book, because we are writing arguments first followed by functions like this, x for us, xf means the functional value of f at the input x. So that's why we start our calculation from here, because our input lies here. Whatever this does, at least it keeps the order naturally. Like normally we write from this side to that side. There are languages, of course, where you write from that side to this side, but that's a different matter. We write from left to right, so our calculation also is going from left to right. Okay, in that sense it's natural. In this sense it may seem somewhat strange to write xf in place of f of x. Whatever the case is, when you are dealing with permutations and their products, you have to always make sure what of these 2 conventions is being followed in your text. Okay, so let us start. Without further ado, we start with 1. On 1 we apply this one, so it gives us 2. And then on that 2 we apply this, which does not do anything to 2. 2 stays 2. And then this one also does not change 2. And then this one also does not change 2. So 1 goes to 2. 2 goes to 3. 3 is kept fixed. 3 is kept fixed. 3 is kept fixed. 3 goes to 1. This one does not change 1. This one then sends 1 to 6. And this one does not change 6. So 3 goes to 6. 6 is unchanged by the first two, 6 goes to 7 by this one, and this one does not change 7, so 7. 7 like that. Let me just write the others. 7 to 8, 8 to 9, 9 to 1, 1 to 5, that means 9 to 5, and finally 5 to 4, 4 is unchanged by the subsequent ones, so 5 to 4, then 4 to 5, 5 to 1, so 4 cycles back to 1. So this is the permutation as a product of disjoint cycles. In fact, there is only one single cycle, which is a 9 cycle. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. And B, okay, like before, 1 to 2, 2 to 3, 3 is unchanged, 1 to 3, 3 is unchanged by this, 3 to 1, 1 to 2, so 3 to 2, 2 to 1, 1 to 2, 2 to 1, so 2 to 1. So this one is also a cycle. Nevertheless, the single cycle is also disjoint in a trivial and silly manner, because there is no other cycle. And let us solve one more. Prove that the inverse of this n cycle is another n cycle which has the exact opposite order. Note that our original n cycle sense is not a very nice word here, maps I onto J, where I and J of course are among these symbols, if and only if this other n cycle maps J onto I, which you can just simply observe. For example, what we are saying here is that this cycle, not the inverse, the cycle itself maps 1 to 2, this one maps 2 to 1. Conversely, if whatever this one does the exact opposite. For example, here this second one, this n cycle maps n minus 1 to n minus 2. This one, however, if you imagine the elements, the two elements before n minus 2 and n minus 1, This one maps n minus 2 to n minus 1. This one maps n minus 1 to n minus 2. So that is why they are inverses of each other. Hence, the solution that I have written here for this one may not be really that rigorous, but if you want, you can write some other more convincing rigorous argument, but I don't see the point, because one way or another this idea has to be used. Hence, and that's just it. So here I end things. In the next update on group theory, we will solve more exercises and we will go to the more non-trivial and difficult ones. So that's just it. Today is Tuesday, so Wednesday, Thursday we don't have anything. Friday, let us again go back to field theory. So that's it for tonight. See you on Friday with field theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.